So if you're just coming in and get your test turned in, we'll have these regraded. I don't know what time we'll do that. Josh and I have to figure out when that'll be, but soonish, and you'll take your previous test from before. If you got, say, 60, and you get 80 on this one, you can earn half your points back, so you end up with a 70, right? And we'll do that instead of a curve. So that'll be posted sometime this week for sure, hopefully pretty soon. Okay, we're going to pick up where we left off last time. Last time we just talked about there were some theoretical models that estimated what your theoretical strength should be, and we walked through those, and basically we're finding that we are a couple orders of magnitude lower, right? We expect 44 gigapascals, even in the very best materials that we can manufacture right now, like really thin fibers. I mean, this is fibers, that's really like a whisker. It's a tiny, like, smaller than micron, a lot of these things are. That's maybe half the strength, and then actual materials are a couple of magnitude lower. So what's the reason for that? I think right as we ended class, we said, well, there's got to be flaws, right? There must be something that's reducing your strength, or rather, maybe the right way to think of it is that locally within your material, you have something that's greatly magnifying the stress, right? They call them stress concentrators, where it just causes your stress that you think you're applying to get greatly magnified, right? So if you think you're applying sigma naught, you saw this plot in 2010, you're applying sigma naught across the whole material, which takes into account the force of the cross-sectional area of this whole material. But locally, if you have a flaw, the stress actually spikes to some much higher value, right? And so you actually have sigma m instead of the sigma naught that you're applying. Therefore, if you took sigma m and divided by sigma naught, it'll give you some number greater than 1, 4, 5, 10, whatever it is. That's your stress intensity factor, right? So your flaw gives rise to a stress intensity factor that's greater than 1, therefore your material breaks at a much lower strength than you expect. So how do we account for this? What causes it? Well, things that affect it, the shape of this flaw, if it's a pore, right? It could be the shape of the pore. So what's going to be the worst would be a very high curvature, which means a small radius of curvature. So a flaw that looks like that, a really sharp one like that, is going to be more damaging than a flaw that would encompass, say, the same volume but is circular, right? That would be far better case to have, would be this one. Right? The presence of cracks or grain boundary cusps adjacent to pore, right? So if you have a grain boundary right here nearby a pore, that's going to be more adverse in terms of strength, right? Now, why is that? Any thoughts? Why would a crack or a grain boundary near a pore be more adverse than far away? What do you think, Ashley?
Doesn't it allow the cracks to travel?
Yeah, because what can basically happen is that your pore can break the rest of the way there, and now this whole thing can be thought of as one long crack, right? So yeah, it gives crack motion, absolutely. The distance between a pore and then the pore and the surface, between pore to pore or pore to surface, is also damaging for the same reason, right? If you have your surface right here, and you have a pore right there near the surface, we know that cracks at the surface are the worst, right? But in this case, very, very close to the surface is actually even worse than at the surface. Why? Well, because once this breaks, now your half crack length is that big, right? It's worse than even if this was right at the surface, then your half crack length would be just less, right? So a weak area makes it even worse because once that breaks, you have a larger crack. The size and shape of inclusion. So now we're not talking about pores. An inclusion is something like a secondary phase, a speck of dust, right? An eyelash that fell out of your eye when you were working on this stuff. Like these things, there's evidence. Like actually, later on in the book, he talks about quality control, and he gives an example that somebody's eyebrow hair fell into a ceramic, and they were trying to figure out why they were breaking, and it was something as simple as that caused them to break. So. And then the difference in elastic moduli and coefficient of thermal expansion between the inclusion and the matrix. Why does that matter? Yeah, what do you think, Barrett?
So if you have an inclusion that has a different coefficient of thermal expansion, it'll be like it's going to be obviously differently than the matrix that it's within. So that itself can inform surfaces and areas for cracks propagate.
Yeah, absolutely. So CTE makes sense, right? If something expands less or more, it creates either stress or compression, right?
Sorry, dumb question. What's an inclusion?
An inclusion is something that you don't expect to be there. A second phase that you didn't intend to be there. Maybe you did intend, but it's a secondary phase rather than the host material. So a precipitate is a type of inclusion, but but not all inclusions are precipitates, because a precipitate is something that spontaneously precipitates it. It segregates out to the secondary phase. An inclusion could be a speck of dust that fell into your bath while you were making it, right? So it's a secondary phase. It's generally speaking undesired, right? Now what about elastic moduli? Why is there a difference in elastic moduli? What does that matter? Any thoughts? Elastic moduli tells us what about a material? Stiffness, right? It tells us the stress-strain response, right? Yeah, what do you think, Jason?
So I guess if you have different elastic moduli under different stress and strain, it could break in the center, which would then cause more fractures to radiate outward. If it would be more brittle.
Yeah, I think you're saying it correctly there. Barrett, you have something to add?
Isn't that sometimes though a desired thing, like in composite materials, we want that?
Yeah, so take this scenario for a minute. Let's say you've got your bulk material, you've got some secondary phase, some inclusion in here, right? Let's say that this thing, the modulus of the precipitate is much greater than the modulus of the host. Now you apply a stress to this whole thing, what's going to happen? Well, you apply stress, that means that you're going to get a strain, right? Right? You're going to get a strain. Now, what's going to strain more, the host or the precipitate? Since the modulus of the precipitate is higher, that means that you have to apply more stress to get the same strain. Therefore, the host is going to want to shrink more, right? And this is not going to allow it, right? So that's going to create a boundary, right? A stress at the boundary, the interface between these two things. So if you are going to have a secondary phase, you'd like its moduli to be more or less matched to the host if you don't want to create those stresses. Maybe you want those stresses, right? It might be that you want a certain amount of stress, not enough to break it, but enough to create a large strain field around it, which will then influence things like diffusion, right? Or dislocation motion, right? So that might be desired, but that will lead to some stress, right? So all these things can lead to stress magnifying, right? So the way that we account for this is with fracture toughness equations, right? So Griffith's fracture toughness equation, we talked about it in 2010, so I'm not going to spend a lot of time. I'll just remind you the basic equations right here, right? K1C is a fundamental materials property. It's the fracture toughness of a material. We write it as K because it's the same K as stress intensity, but now it's just saying there's a critical stress intensity for mode 1 fracture. Mode 1 means you've got a material and you're just pulling it apart from the end, right? You're not twisting it, you're not bending it forward and backwards, it's just you're pulling it straight apart. That's mode 1 crack, right? Good. And then the C means critical. So it's a critical stress intensity factor for mode 1 crack growth, right? And it basically says Y, your geometric constant, which again, for this class, we're going to use 1.12. The book says 1. I disagree with him on that. Most books say 1.12, right? For the plane strain condition, you've got your stress at which it fails, the critical stress at which it fails, times the square root of pi A. And A is usually written as A sub C as well, meaning a critical half crack length. Okay? How is this useful? Well, you can take an example like this where you have a flaw in your material, and if you know the fracture toughness, and you know the size of this flaw, you can calculate what stress this thing will break at, right? When you look up a spec sheet, it says the yield strength of this alloy is 500 MPa or 200 MPa. That's just not a very good metric because that doesn't take into account any of the flaws that are present or how your flaws might emerge in the material. It's just saying as we make it, we find that it breaks around this level, right? Okay? So this is great. If this material was steel, steel has a fracture toughness of about what? What are some average values of fracture toughness that we should know for materials? Polymers versus ceramics versus metals. Rough ballparks? Really brittle materials like ceramics, where are they at? So K1C for ceramic is going to be somewhere less than 10 megapascals root meters, right? If it's greater than 10, it's the exception to the rule. And there are some ceramics, but that's the exception, right? What about polymers? Yeah, most polymers tend to be pretty brittle. They're also in sort of this less than 10 category. A lot of them are even a lot less. What about metals? Greater than 10 is not a bad way to put it. Steel, for example, is a very tough material, and it's around 50. Aluminum is a little bit less. It's like 30 or 40, right? So if this was steel, right? If this was steel, then it's 50 megapascal root meters, right? Let's say that we're going to apply a stress of, what's our stress we want to apply? 100 megapascals? Assuming that we can call the geometric parameter for this 1.12, then what would be the stress at which, or what's the largest flaw this thing can tolerate before it breaks? Right? Let's actually type this out. What is it? Okay. So K1C equals Y times the stress square root of pi A. So we've just said that we're going to use 1.12 here. This will be 100 megapascals. You got 50 megapascal root meters. So what can A be? Somebody want to calculate this for us? So, I think I brought my calculator.
Yeah. 6.3 centimeters.
6.3 centimeters? Did I mess up something? Oh, I gotta take the square root of this. Or I gotta square it, sorry. Yeah, so I get 6.3 centimeters, because this is in meters, right? As I put it in, everything it was in megapascal root meters. Megapascals cancel, and you're left with just root meters. When you take square, that's the answer in meters. So 63 millimeters. So that's saying your flaw can be 63 millimeters big. That's a huge flaw, right? That's a monster flaw, but that's because steel is a really tough material, right? So what would that same material be if this was a ceramic, right? So let's assume it's a ceramic with a fracture toughness of 8, right? How's that going to change? Well, then our flaw can only be 1 millimeter, 1.6 millimeters big, right? So there's your difference. Huge difference in materials in how they respond to stress, right? 63 millimeters. And then if K1C equals 8, the critical flaw size is 1.6 millimeters, right? So clearly ceramics, since they have a low fracture toughness, and like I said, 10 is on the high end, right? Like single crystal, like silicon, when you grow single crystal of silicon, that's probably like 2. I don't know, we could look it up in the book, but it's gonna be super low. They're basically totally intolerant to flaws. And any flaws, because we're starting to get quite small now, will cause them to break. Yeah.
Now, is that just mode 1? Because you know, like, ceramics can be compressed a lot. So does that change?
Yeah, this is mode 1. This is pulling it apart. So you don't typically use Griffith's fracture toughness for compression. Why don't you? Is because it's actually kind of interesting. Actually, if you look at, and I'll show you guys a picture of it. We'll do it right now. What happens? If we scroll down, if you take a look at what happens during compression testing, first off, they explode. So you have to have a camera that can capture this. Like this is microseconds, right? But take a look at this. Some of these are vertical, but you'll notice that a lot of them are actually at 45-degree angles, right? So that, and maybe the mechanical materials class you're talking about this, right? What's happening is that actually fails under shear. That 45-degree, that's because that's where you maximize shear, and it actually is much weaker under shear than just actually smashing bonds together. That'll make them slide past each other in shear. So you'll see things actually switch. They go to 45-degree angles. So now you're definitely not going to use mode 1 fracture toughness. You're breaking it in a very different way, right? So do they use Griffith's fracture toughness for compression? Probably. I don't think it's super common though. All right, so sharper pores, greater stress. Pore crack combo, we talked about that already. Pore clusters give the same effect as having a larger pore, right? If a bunch of them are clustered together and just a thin skin of materials connecting them, that can break easily. Now you've got what looks like a big pore in the material, so that's not good. Cares about that. All right, surface flaws are very detrimental. Why? Well, because when we talk about Griffith fracture toughness, This is our half crack length, and if it's a surface flaw, then the whole thing is A. If it's not a surface flaw, say like right here, that whole length of our flaw, since it's not touching a surface, that's 2 times A, right? So the entire flaw is 2 times the half crack length. If it's at the surface, this half crack length is the length, right? Therefore, a surface flaw is doubly bad, right? As we've drawn this thing is about as big as that thing, roughly, right? But this thing, the whole distance of that's 5 millimeters, that's all equal to A, whereas this thing that's 5 millimeters, the half crack length is only 2.5. So this is far more severe. And so with dealing ceramics, if you can fix stuff at the surface, which is nice because that's stuff we can fix, you can't fix stuff on the inside very easily, it's to your advantage because it's also the worst type of crack for you. So some examples of that, even if you touch a ceramic, a pristine ceramic, when you touch it, they've shown this in a paper that it went from 10 to the 5 psi down to 10 to the 4 psi strength. So just touching it caused something to happen to the surface that weakened it, right? If you subsequently etch it with HF for glasses, then they restored the original strength and that removed surface cracks, right? So an example, commercial glass rods, when you buy these, in the book it's talking about them, their as received strength was 6,500 psi, right? When they sandblasted these, that dropped by over a factor of 3 down to 2,000. And when they acid etched it and lacquered it is just filling in any cracks on the surface, and acid etching is getting rid of those cracks in the first place, it jumps up like more than an order of magnitude, right? Almost 2 orders of magnitude. So surface, controlling the surface of your ceramics is enormously important for your strength. Like, this blows me away that it made it that much stronger. Just really remarkable, okay? You get microscopic dirt particles on glass really frequently, and if you look at where it breaks, when you break these things, well, I think we're getting to that later, you can see these things right at the surface that they caused the failure. Now, why? It could be a chemical attack. It might be a CTE mismatch, right? As this thing stuck to it and then expanded at a slightly different rate. Any of these things are causing you to have a failure point on the surface. Okay, skip that. How do you test then ceramics? It sounds like you learned about this in MPS. But the way we test ceramics is under bending. The reason why we've covered it in 2010, if you grab onto these things, if you took, vice locks or whatever, and you clamped onto this, where those teeth bite into it, it's just going to break right there. They're just totally intolerant to strain, even small amounts of local strain from like vices gripping it. So instead, you take your ceramic and you bend it, right? Do I either do 4-point bending or 3-point bending, right? What's interesting is that you can apply the exact same load in both of these scenarios, right? And you get different strengths, right? The sample dimensions can be the same, the span separating it, all that could be the exact same, but if you have one load here with the same load split over 2 here, you get very different failure rates. We talked about this last time. Somebody recap why you get different failure strengths. Anybody remember? Yeah, we can go. Or Jake, sorry.
If you're applying it at a single point, you're essentially forcing all of that load onto a single plane within your ceramic.
Yeah, when you say load, you're talking about bending moment, actually. The bending moment goes up, and then it goes down. In statics, you would have, when you learned about the maximum bending moment. That's what you're saying, okay?
And then when you do 4-point, you have that load is essentially spread out between those 2 points rather than this.
Yep. If you were to plot the bending moment, which is proportional to the strength of the material, right? You get a larger region. You get, I don't know, say 6 millimeters versus just one spot, right? And so then, why does that influence strength? So your maximum bending moment is whatever the value is here, or you reach the same value there, so why do you get different strength? Doing that.
If there's a flaw in the middle of those two, it's going to more affect the strength.
Yeah, consider for a moment like your critical flaw size is like right there. And the same flaw exists in both materials. Well, this flaw has about half the bending moment of that one, right? So this one will cause it to break. Therefore, it's a statistics thing that says that the volume of space inside your material where a large flaw is present is higher for the 4-point bending. There's better odds of you getting your max bending moment at a flaw present. So even though these are the same material made the exact same way, if you test them in 2 different setups, you're always going to get lower strength for 4-point bending because you're exposing a larger volume to the higher bending moment, right? But this is typically how you test ceramics. It's a nice way to do it because these are just rollers, like they're metal rollers that you set this on, so there's no surface damage, or you're minimizing surface damage while you do the testing. If you went ahead and did this, you can calculate what the strength would be. It's not a typical tensile strength, right? It's bending moment. It's modulus of rupture or the bending moment, right? You'd need to know what the moment of inertia is. You guys learned about this in statics. In this class, you're just going to look up formulas, right? I'll tell you where to go and find it, but you would just test it by looking it up. Okay. The book has these in greater detail. Okay, we talked about compression already. It's another common way to test things. Typically with ceramics, strength for compression is something like 10 times the strength under tension, 10 to 15 times, right? So the same ceramic material, if you can choose to load it under compression or tension, you're going to choose compression because it's about 10 or 15 times stronger. Right? There's also this concept of biaxial strength. This comes from the book. So if you take some sort of indenter, right, and you apply a load straight down on it, then you're going to get some sort of usually tension versus compression. Here's like your stress that it's going to create, right? Since it's not exactly a single point, it's not a spike, you're actually going to get a distribution of stress that might get something like that. The actual volume of that will depend on the elastic constancy of the material, but it looks about like you'd expect it to. You know, it's interesting. You apply that same load, but now you drag it this way, right? So now you have a biaxial stress condition. You create this in terms of your stress profile. It's really interesting. So these F values represent different coefficients of friction. Obviously, friction is going to put this dragging force on it. So this is interesting. In front of it, if you're pushing it that way, right, you get a really high spike in compressive strength in front of it, and you get a really high spike in tensile strength behind it. So if you do this, where are your cracks going to form as you do this to a ceramic? So we're moving it that way. So compression is where it's the strongest. It's the weakest in tension. So it's actually going to leave a wake of cracks behind it. It's very, very common to see. So when do we see a scenario like this? Do you ever see this? Do you even care about it? Like, it's like fine if it's an academic exercise, but do you see this in the real world? Do you see times where we can do this?
Yeah.
Where?
Ceramic ball bearing.
Yeah, ball bearing, sure. Other instances? Anybody polished a ceramic before? Right? With your like silicon carbide paper or anything else? In 3010, you guys not polished anything? No. So polishing is exactly this, right? You take a wheel that's spinning, it's sandpaper, you take your ceramic, you push it down on it, you've got water flowing, so it cleans that gunk away that you're removing, right? But you're pushing down and you're forcing it across. So as that piece of silicon carbide on the silicon carbide paper cuts through your material, it's leaving behind it a wake of cracks, probably, because you have this spike in, and what's the coefficient of friction between a ceramic and silicon carbide? It's going to be pretty high, right? So you can put a lot of lubricants on there, and they run water typically, right? To try and minimize this post-spike afterwards, but you're still going to have a high likelihood of trailing behind cracks behind it, right? So you polish it, and you're leaving behind cracks where you polished it on the surface. So polishing is it's a very damaging process when you do it. Okay, we'll come back to that later. Strength degrades at higher temperature. For all materials, pretty much, strength degrades at higher temperatures, but ceramics are better. Yeah, Jace?
So I guess for that last one, so could you technically go and fill those cracks?
Yeah, absolutely.
Afterwards, just to make it increase the strength of the material.
At some point, yeah, in chapter 15, we talk about machining. We'll talk more about that. But yeah, so it's interesting. It's this game we have to play because on one hand, let's say that you have a big gouge in your material from something. You know that's going to reduce the strength. It's a huge half crack length right at the surface. So you want to polish it to get rid of that. But as you polish it, you introduce a bunch of really small half cracks and these surface damage and from the trailing wake. So you have to try and fix that. So if you saw what they did up here, they did, where did we talk about it? Right here. They did acid etching. That's like a type of chemical polishing. It's not going to bind the cracks, but it's going to etch some things more than others, right? So you're still not going to have a perfect, nice, flat surface. And then they lacquered it, right? A lacquer is basically filling that in. So that's a great thing to do to increase the strength of your material because when you machine things, you just massively damage them. It's really small, so we don't notice it, but there's a lot of damage there. Okay, ductile versus brittle. In 2010, we talked about this, that some things we think of as being ductile, plastics, right? These things are super ductile. You can stretch most of them unless it's cold or a high strain rate. Plastics tend to be really, really plastically deforming, right? They can stretch quite a bit. Metals, we know the same thing. If you take a bar of aluminum, for example, and start stretching it, it'll stretch quite a bit relative to ceramics. And ceramics basically have no strength. They can essentially accommodate no plastic deformation. It's so small that we usually say nothing, right? Talked about how that works in 2010. Basically, how does plastic deformation occur? Via dislocation motion. A dislocation is something like this extra half row of atoms here, or you can think of it as a screw defect where if you do like a parking garage, these things don't match up. It's like cycling up and further out. So you gotta have a screw dislocation or an edge dislocation. I'm not gonna go into great detail on this because we already did in 2010. But as these things move, that's how you get plastic deformation, right? So what is our rule for making material harder and stronger? What do we do to dislocations? What's that? You can either increase them, have more of them. Why does that make it harder and stronger? Because we just said these things moving, it makes it plastic. So adding lots of these things, shouldn't that make it easier to move? Yeah, that's what happens, right? They start to see one another because this thing, that extra half of atoms, that obviously creates a strain field of extra compression up here and tension down here. Those start to see one another, interact with one another, and overall limit their mobility. So you've made it harder and stronger. Talked about that already. So why don't ceramics, you can still have dislocations moving. Why don't they move them? The answer is that they don't have good slip systems. What was a slip system in metals? Do you remember a slip system? What is it composed of?
Planes.
A plane? Yeah, you have to have a plane and then you have to have a direction, right? So these planes are going to slide past one another, right? That's a slip system. So, you got a ceramic, right? You can imagine like a densely packed plane, probably along like this plane. You got a densely packed direction, like that direction. Why can't these things slide past each other, right? Well, the problem is, even if you do identify a slip plane, why don't they slide past one another in ceramics? Anybody have an idea?
Common in ceramics, or depends on its brilliance.
Be a good guess. Actually, they can. You can have a really symmetric, like rock salt. Rock salt's super high symmetry. You're going to get a ton of really high density planes. Like it should, from a slip system perspective, you'd think, hey, this should be slipping. Wait, the bonds are just too strong. High bond strength. That's one thing. Meaning, when you start sliding this thing is going to have to break bonds with that thing, right? When you slide it, and that's a really strong bond. That's part of it. That's not even the main reason. What do you think, Chris?
And just going on with that, against their covalent bonds, so the electrons are very localized. When you try to slip it, they don't kind of go with the atoms.
Okay. If it's a covalent bond, right, those electrons are shared very tightly, and breaking that bond, sometimes it's so exothermic that it just says, I've generated so much energy, it's easier for us to break now, right? The real reason, even in ionic systems where you don't have that happening, is look what has to happen. As this thing is sliding past one another, right, it has to go from being a negative bonded to a positive, which it likes, and it's very close to those two. It has to slide past negative to negative, positive, positive, negative, right? So there's massive electrostatic repulsion as it does this. Metals, they don't care because metallic bonding is just sharing and C electrons. If it slides closer to another metal, that's great in terms of bonding. It doesn't mind that at all. But this is an extremely negative intermediate state. And so for this to happen, you have to have a really high temperature to accommodate this strong repulsion, right? Otherwise, it's just happier just to break. And that's what happens. Rather than sliding past one another, ceramics just break, right? The electrostatic repulsion is just too strong. Okay? That's the last thing for here. Let's switch now to chapter 9. Any questions on chapter 8? Straight stuff? So chapter 9 deals more about, strength is one thing it talks about, but it's generally these time, temperature, and environmental effects and how these influence properties, right? So we're going to talk about creep, slow crack growth, chemical attack, mechanically induced effects, thermal shock, right? So let's do creep first. I think I talked about this for sure in 2010. I'm not even showing this picture where it's a roof, and you can see what's happening to this roof is that over time, it must be supported mostly at this end and at that far end, right? With less than adequate support in the middle. And so what's happening? Creeping, it's bending, right? Creep is something that doesn't happen instantly, and it's always happening, but the rate is so slow that you don't see it, right? You need to take into account time before you see the plastic deformation. Technically, if I take this pen, right, and I pull on it, it is stretching a little bit in response to whatever its stiffness is, but that's more or less an instant stretch, and I let it go and it instantly goes back a little bit. This is something where if I were to pull on this for 7 years, it might slowly start stretching. And by the end of 7 years, you recognize, hey, you're a millimeter, right? So it's really slow. You can think of it as really slow plastic deformation. It's got to be plastic, though. This is non-reversible. If you took this roof and you turned it upside down, it's not like this thing would instantly go right back up. It would start creeping and slowly creep all the way back up, right? So it's permanent deformation. It just happens really slowly, okay? And typically we think of it as being under constant stress, right? So the weight of that roof isn't really changing. I guess snow goes on and off, but it's basically not changing, right? So it creates a curve that looks like this. Plotting strain versus time. When you apply your load at first, when they first built the roof, it's going to stretch a little bit, right? That's the elastic stretch, right? So elastically it's going to deform, right? But then all this strain from here on out is all plastic. There's going to be a region where it's rapidly increasing up to a point, and then it reaches this is primary creep. It's going to reach a region where it's now constant rate of creep. That's the steady state region. And right before it fails, it starts to take off again. So there's these 1, 2, 3 regimes that are characteristic of creep. Okay? It'd be great to model all 3 of those regimes, but it's hard to. So instead what we model is the second regime, right? Because it's linear. It's something that we can control a little bit. So you could say, hey, if you know the slope here, and this is typically a log plot, yeah, it must be a log plot actually, then it might go from, I don't know, a couple days to 5 years of the material, right, before it breaks. So this is a nice time to be able to model what creep is doing there. So how do we model it? First, let's talk about what causes motion, right? There's 2 barriers to dislocation motion. First off, you can have things that have long-range stress fields, so something like more than 10 atomic diameters, and this could be a large precipitate, another dislocation, some sort of athermal obstacle, so like inclusions would fall in this category, okay? Or you can have things with shorter range stress fields, right? So point defects, for example, can do that, right? So those are both going to prevent dislocation motion. The expression for our steady state creep strain rate is right here. So epsilon with a dot above. Anytime you see a dot above it, usually means a rate. So it's strain versus time. It's how strain's changing over time. D epsilon dt, right? It depends on A and N. These are both constants. Q sub C, that's our activation energy. That's a constant for material. And then it depends on the stress and the temperature, right? And you can see if you want to increase stress, you're just going to increase strain rate. If you increase temperature, since it's in the denominator of a negative exponential, that's going to increase strain as well. So essentially you get plots that look like this. Your strain versus time as you go from low temperature to high temperature, going that way, right? So the same strain is achieved very rapidly at a higher temperature, whereas you had to wait many, many hours to get at a lower temperature, right? So heating something up makes creep strain go way faster. Well, the same thing. Low stress, high stress, right? So increasing stress makes it also speed up quite a bit faster. I think we mentioned this in 2010 that you'd like to measure like how long is you want to know the creep of material for a roof, but you can't just build a roof and let it sit for 20 years and make that measurement. You can, it's just not very efficient. So what do we do instead? You take advantage of this. You either increase the load beyond what it's actually going to be under, or you increase the temperature, or you can do both, right? And if you do both, you can determine what these creep constants are, A, N, and Q sub C. Once you know those, you can determine it at any arbitrary stress or temperature, assuming it's that you're still in the secondary creep range, right? So let's talk about how deformation does occur in ceramics. It doesn't occur very easily, but if it does occur, it must be either dislocation climb or diffusional creep, right? So dislocation climb looks something like this. You got your obstacle. Here's your dislocation, see the extra half row of atoms here. It would like to move through the material and cause deformation. But it can't, because this thing, obstacle's in the way, it's got a stress field associated with it, and so this thing can't get past it. So one thing it can do is it can absorb a vacancy, empty spot right here, by this thing hopping over there, this thing can hop over there, and you essentially, in doing so, you move the dislocation up a level. So vacancies can get absorbed, and you can move your dislocation. If you get this a couple times, you can pass whatever's blocking its path, right? So that's why we call this dislocation climb. It has to climb out of the way of what's in its path, right? So obviously you're requiring diffusion. This atom has to hop here, right? So atomic motion requires diffusion. For diffusion to happen, you have to have temperature, basically. So this is not something that's going to work very well at low temperature. right? In fact, the rate at which it occurs is given right here. Here's your strain rate for diffusion climb, or dislocation climb. It's going to be proportional to your diffusion coefficient, stress. It's going to be inversely proportional, so the bigger the Berger's vector, the slower it's going to be. That makes sense. This thing has to hop some Berger's vector distance away. If that's bigger, it's going to be a slower process. Shear modulus, the N is the dislocation density. So if you get too many dislocations, they're going to start to see one another, and it's going to slow this down, and temperature in the bottom. Why temperature in the bottom is actually interesting. It has to do with mobility. Normally you think higher temperature, you should go faster, but we're actually talking about this in, if we look up Einstein mobility, Einstein bagels, Einstein diffusion equation, no, there's a wiki page that's better. Right here. So what we really care about is not diffusion coefficient, what we care about is mobility. And so you saw diffusion coefficient was in that expression. That's because the total rate should be proportional to the mobility. So all they've done is they put D in the numerator and KBT in the denominator. So that's why temperature is in the denominator, even though you think, hey, temperature should be a good thing. It's because mobility is what we're really after. Then the second one, this one's interesting, is diffusional creep. So if you take Shetty's ceramics class later on, you'll learn more about this, but we'll talk about it now. Nabarro-Herring is one type of diffusional creep model. And how it works is really pretty clever. Essentially, you get self-diffusion. What's self-diffusion mean, as opposed to any other type of diffusion? Yeah, you've got like pure iron lattice, and for some reason you've got iron hopping in there, and if there's diffusion, maybe there's like a net flux from one side to the other. So there must be a reason for iron to hop into iron lattice, right? It's not being driven by concentration gradient without some sort of something else happening. So what is that something else that's happening, right? So atoms, we're going to find out that they tend to move from grain boundaries under compression towards grain boundaries under tension, right? So you got this example here, right? I apologize, it's hard to see, but you're pulling this thing, right? If you're pulling it and you've got a compressive stress going that way, then we just said atoms move from grain boundaries with compression. So atoms over here move from here towards regions of tension. And why on earth does that happen? Right?
Strengthen the material.
To strengthen the material.
Yeah, it goes because from compression to weaker point. So
okay, that's an interesting point.
That to the tension area to naturally increase the energy system, I guess.
To do Jacob Barrett.
You're pushing the atoms closer together in compression, so they don't want to be that close, and they move.
Yeah, that's a great way to think of it, right? If I took like this row of students and I start like squashing it, right? Ashley and Jane are going to be starting to get real crowded in the middle. They're going to diffuse out to the edge of the classroom. That's exactly what's happening. And the same on the same regard, if there's bonds right between atoms, and I start pulling this row of students this way, Ashley and Chris are like, no, moving away from each other, right? And sooner or later, someone's going to swoop in and like fill that gap, right? We know that atoms have like an average distance where they want to be bonded, right? If you squish it or pull it apart, they're unhappy. And so if they're unhappy, that leads to what? The right way to think it. So you guys said it totally right. Did you have something you want to add there?
That was it.
Yeah. So you hit it right on the head. Mathematically, what's happening is there's a vacancy concentration throughout this material, right? Any material has vacancies in it, right? Some concentration. It's usually really small, right? If you remember, even close to the melting point, it's like 1 in 10,000 atoms are missing. So we're not talking about big numbers here. But there's vacancies everywhere. The vacancy concentration is C, right? We're going to modify it when there's a stress nearby. If there's a tensile stress, here's your initial value, C naught, right? That's what you expect it to be with no stress. But our actual concentration with stress is going to be exponential of the stress applied times the average atomic volume, that's what capital omega is, times divided by KT, right? So basically that's a positive number. So under tensile stress, this is a number greater than 1, you're going to get more vacancies, right? That makes sense. We just said as you're pulling something apart, you should be creating more vacancies, right? Meanwhile, under compression, it's the same thing, just negative. So you're compressing it, you should be getting rid of vacancies. You're squashing them together, right? So now, near tension, you have more vacancies than you have near compression. So you got a gradient composition in concentration, right? More vacancies, less vacancies. Vacancies are going to move that way, and for vacancies to move that way, that's just mass flowing the other way. So this is really interesting. If you take a material and you apply a load and you leave that load stuck on it for a while, what you're going to see is the microstructure actually changes. Things went from being like a nice equiaxed grain. You could have this sort of situation before where they're like, let me draw it the right way. Where they're sort of like equal shaped. And if you apply a load on this for a while and let it sit, what will it look like? Well, the load's not changing direction. Mass is flowing here and it's flowing here though. So what will these grains start to look like? What's that, Gabe? Yeah, they're going to start to stretch out. You're going to get things that look kind of like, how do I draw this? I'm not tried to draw this before. Kind of like that maybe, right? They're stretching more vertically, right? Because it's going to squish in from the sides, it's going to grow vertically, right? And what that's going to do if you have this happening over lots and lots and lots of grains is that you're actually going to get creep. It's actually going to change dimensions a little bit, right? So Nabarro herring creep is an important ceramic type of dislocation mechanism. Just because there's not anything else. You can't have dislocations moving, so how do you achieve deformation? Sorry, a deformation mechanism is Nabarro herring. So you can write a similar expression for it. There's your strain rate. It's going to depend on slightly different things, right? Before the average atomic volume didn't matter in our previous expression for dislocation climb. Now it does matter, right? V or grain size now matters. So it's slightly different expressions, okay? There's also grain boundary creep. So you're applying a constant load, you've got grains. They can start to slide past one another or change rotations a little bit, right? So even without diffusion, you could go from this picture to that picture without diffusion if these grains are able to slide past one another or rotate a little bit. So that's another mechanism in ceramics that can happen. Okay. There's twinning, which we talked about in 2010. What we're really getting at, though, is this. So Ashby, a very bright guy who's at Cambridge, I think, he came up with this plot. And what it's showing, it's a deformation mechanism map, right? So as a function of homologous temperature, that's the temperature divided by the melting temperature. So you can make this for all materials because you know the melting point, right? You plot it against, it could be tensile stress, it could be shear stress, it could be whatever, right? In this case, they've got shear stress divided by homologous temperature. And what you see is that there's regions, just like a phase diagram has regions of the map, right? Up here you get flow via plasticity, right? You get deformation via plasticity. Down here, it's all based off of diffusional flow. And it's either oxygen motion, magnesium motion, mix, I read those, right? But these are actually very nice diagrams because you can know at whatever temperature or stress that you're at, what's going to be the mechanism whereby most of your deformation is coming from, right? Which is good to know because if you know that, you know what the different equations are in these regions, you could estimate the rate at which you're going to achieve strain or deformation, right? So these are nice. How do they create these? Well, we just showed you an expression, right? We showed you an expression for strain right here, for Nabarro creep. How would you create these diagrams? Well, you take these different expressions for your different type of creep mechanisms, and you start setting them equal to each other and solving for these different variables, like temperature or the applied stress, right? So that's literally how they make these things. So it's different than a phase diagram, but it can be used in much the same way. Any questions on these, on deformation mechanism maps? No? Okay. So obviously you can achieve creep in polycrystalline materials, we just showed you. It can also happen in single crystals where there's no grains. It can happen in glasses, right? Even high purity glasses. All these things can have time-dependent deformation, but it's going to be different mechanisms. Let's skip that. How do you measure it? How would you measure creep? How would you measure creep? What do you think, Barrett?
See, basically just how much something you form based on the dynamic size.
Yeah, so you're basically saying in what they call an interrupted test. So you're going to leave it under some condition, take it out, make a measurement. Yeah, that's a fine way to do it. If you're at a temperature where a strain gauge can be applied without it, burning off the epoxy, you can do that too. And you can get real-time measurements that are in situ, meaning during the test. You can also do laser, I think we talked about. So we talked about some of these for one-time measurements. The same things can be applied to strain. We are often talking about really long tests. Okay? So one thing he points out in the book is that in a material, even in the same nominally same type of material, you can have huge differences in the rate of creep, right? Here he points out that there's 6 orders of magnitude in creep rate as you process it in slightly different ways, right? So if you start with a high purity material, right, when you're first making it, but then you might add sintering aids. Sintering we haven't talked about yet. We'll talk a lot about it later this semester. Sintering is how these particles coalesce together. Sometimes that's really, really challenging, so we have to add things to make that easier. So if you add sintering aids, that might form a high melting glass, for example, right? So that's going to change things. You could do hot pressing or reaction bonding. You could replace those with hot isostatic pressing or overpressure sintering. All these things are going to influence creep. You could have grain boundary phases that either convert to a crystalline phase from this glassy phase, a high melting glass phase that was at the grain boundaries. That could get converted to a crystalline phase via heat treatment. Your microstructure can be modified to have elongated or intertwined grains. So every one of these things, he talks at great length about silicon nitride, how they all really, really influence the creep of silicon nitride to the point where on 6 orders of magnitude, that's an enormous difference in creep rate just based off the different ways it's processed, right? Okay, there's another time, temperature, environment factor, and it's called static fatigue. Static fatigue means you initially had flaws that are small, you put in some sort of service environment, and they grow. And they grow large enough that they now satisfy the Griffin's fracture equation, right? And there's lots of reasons they can do that, right? So as with creep, static fatigue is influenced by temperature, stress, elastic phase, porosity. All these things influence it as well. And a specific type of static fatigue that we should be aware of in ceramics is stress corrosion by water. This is fascinating. Stress corrosion by water, it can be other chemicals, but water's everywhere, so it happens all the time. It causes the tip of a flaw, so maybe like your surface crack had a really sharp flaw. It causes the tip of that flaw to experience accelerated crack growth because it dissolves, right? The solubility or the chemical reactivity with some material at the crack tip causes it to dissolve faster. So basically you had this. You had your material, right? Your crack length was A, since the surface crack, that's your half crack length. But what's happening is that even if there's not like air like underwater or water like is underwater, there's a little bit of water vapor and air, right? And thermodynamically on small surfaces, water will condense right here, right? So you'll actually get water right there. So that thing is all now water. And if your material, you don't normally think of ceramics as being soluble in water, like salt and stuff is, but a lot of ceramics, like alumina, you wouldn't think of them as being soluble. But in fact, under really, really high curvature, small radius of curvature, you can get local solubility such that you start to dissolve all that area, right? And so your crack grows on a material where you'd never expect a crack to grow. You think that this thing's like solid, it's in air, you don't understand why it's growing. And then a little bit while later, you realize this thing has actually grown, and it could be due to just water being present because it's dissolving it, right? So that's a really big problem. In fact, and every year I think about this, too late, but if you're breaking glass, quartz, for example, is really bad at this. If you're breaking it and you scribe it with diamond, and you go to try and break it in class, it's actually really hard to do. It depends on how thick your tube is, but it can be like hard to break by hand. You take that exact same thing after you scribed it, and just lick your finger and like run along that crack's edge and get a little bit of water in there. You can pop it really, really, really easily, right? So stress corrosion is really important for ceramics. Think of a bioceramic. Think of like your grandma's hip, right? The YSZ that they put in your replaced hip. Now that's in a very wet environment, warm temperature. Your failure mechanisms are just going to be very, very different than what they were in air or under vacuum, right? Just super different situation. We already talked about in 2010 that as you cycle something, as you apply a load, take that load away, apply that load, take it away, you're basically having the elastic regime. Right? Remember, like if this was like a bunch of students, if I grab this row of students and I pull it out a little bit, I'm stretching those bonds, and when I send it and I put it back, it's going to allow those bonds to go back a little bit. That process of stretching things creates accumulative damage, right? You can see evidence of it when you look at fracture surfaces that have lines like this, right? We call these beach marks or striations, but basically this crack didn't fail instantly. This was probably in some sort of rotating or whatever continual cyclic stress situation, and you see the crack slowly inch forward. And then even more interesting, look at this here. Your crack stripes are so small together they're like hard to see. But out here, you're seeing pretty big stripes. So what's going on there? It means that as the crack got bigger, the rate of crack growth also got bigger, right? And that's not surprising. We learned about that in 2010, right? Here's our fatigue crack propagation rate. So the change in the crack size with respect to the number of particles, or with respect to the number of cycles, it gets larger, right? It's getting slowly larger. It's increasing. So the rate of crack growth is slowly increasing. Okay, we'll pick up here next time and finish up chapter 9.